So our next speaker is Ángela Capel. She's also with the Technical University of Munich. Today, she will talk about entropy decay for Davies semigroups of a one-dimensional quantum lattice. Ángela, please.
Okay, thanks a lot for the introduction. Let me just check. Are you seeing my screen?
Yes. There are some gray box.
Hi, can you hear me?
Yes. I think there's a chat box on the right up corner. Can you see there's a box there?
This thing, you mean? This is the...
Yeah, just can you minimize the box?
Okay.
So on the left, there should be a... Yeah.
Yes,
yeah.
sorry.
It's better.
This, yeah, I'll just put it here. Sorry. Okay, now is there anything?
Yeah, I think it's perfect.
Is there any problem? I mean, is there anything in front of the presentation?
No.
Hi, sorry.
Yes. Ángela, you can go ahead when you are ready.
Oh, okay, sorry. Okay, so thanks a lot for the introduction, Hao-Chang. And of course, thank you very much to the organizers and to the program committee for allowing us to present our work here today. It's a pleasure to be here with you, even if virtually. And today I'm going to talk about entropy decay for Davies semigroups of a one-dimensional quantum lattice, which is a joint work in collaboration with all these people that I mentioned here. So with Ivan, Lee, Angelo, David, and Cambyse, some of them from Munich too, and some others from Madrid and from Paris. And now I'm going to introduce the problem that we are working on here. So sorry for those of you that have already heard this part. The problem that we are interested in working is essentially to estimate the velocity of convergence of certain quantum dissipative evolutions to their thermal equilibriums. And the reason that we are interested on this problem is that, in nature, we know that no experiment can really be executed at 0 temperature or be completely shielded from noise. So we really need to consider open quantum many-body systems to model feasible, interesting physical systems. And when we consider a system like the one that I draw here, like essentially just a square lattice as a simplification, and we consider it inside an environment, and we assume that they are weakly coupled to each other, then there are some simplifications that we can do here to study the dynamics of this system. But what we know from the beginning is that the dynamics of the system is dissipative. So the energy is going to tend to dissipate. And in particular, when we make these assumptions that I was mentioning, which are related to the Markovian approximation, then we know that the continuous time evolution of an initial state, so a density matrix on the system, is given by a quantum Markov semigroup, which is a mathematical structure that we'll see now. So a quantum Markov semigroup is a one-parameter continuous semigroup of applications which are completely positive and trace-preserving, so they are quantum channels. And it's because we are studying all these things in the Schrödinger picture. If we did in the Heisenberg picture, then we would just be considering unital maps instead. And that's just a quantum Markov semigroup. So this is the structure that we are going to be studying here. And the idea essentially is that when we consider a density matrix over our lattice that we are calling lambda, so this is the lattice in which the system is defined, we consider a density matrix on it, and then we let it evolve with time, then this evolution is given by this quantum Markov semigroup. So what we know is that after a certain time t, the state has been transformed into the quantum channel at time t evaluated on this initial density matrix. And this is actually given by the exponential of time and some operator that is the infinitesimal generator of the semigroup. And it's usually called Lindbladian or Liouvillean for different physical reasons. And what we know about this object is that when we assume some further conditions, such as primitivity, so the fact that the generator or the quantum Markov semigroup has a unique fixed point that is actually full rank. And also we assume some detail balance condition. so some self-adjointness with respect to a weighted inner product, then what we know is that when we let time evolve to infinity, we always have convergence to the fixed point of the evolution, to this fixed point that is full rank that I was mentioning before. And this is always going to be denoted by us, by sigma sub lambda. And once we have this convergence, we know that, well, the convergence is guaranteed, but we don't know how fast this is going to happen. So to study that, we introduce the mixing time, and in particular, we introduce the case in which the generator satisfies rapid mixing. And this essentially means that after a certain time t, every density matrix that you consider has already fallen into the ball of center, the fixed point of the evolution, so the equilibrium to which it is converging. And a radius, so this ball has radius that scales polynomially with the system size and decreases exponentially with time. So when this happens for every possible initial density matrix, then we have the property that is called rapid mixing, and that we are interested in proving for certain physical systems. And a way to do that has been studied in the past years is by means of something that is called block Sobolev inequalities, or in particular modified logarithmic Sobolev inequalities, because we are talking about one particular case of this kind of inequalities. And this is essentially given by the definition that I'm writing here. So if you remember the definition of the relative entropy that I'm recalling here, and I'm assuming that everything is full rank all the time, so there's no problem with anything being infinite or something like that, then we can define the modified logarithmic Sobolev inequality constant associated to the generator lambda by the expression that I write here. So it's essentially the infimum over all possible density matrix with support in the whole lattice lambda of the quotient between this term in the numerator and twice the relative entropy between the density matrix and the fixed point, so the equilibrium sigma. And the term that appears in the numerator is actually given by the derivative of the relative entropy when one considers the evolution of rho with respect to the time. So here we see that the generator appears evaluated in the density matrix rho, and here just the difference between the logarithms of these two states. So this is how we define the modified logarithmic Sobolev inequality constant. And of course, when we are considering finite dimensional systems, since this is going to be well defined for the generators that we are considering here, this is always going to be positive. But it might have problems of scaling with the size of lambda, and this is what we have to be careful with. So in the case in which taking the thermodynamic limit, this is still positive, then now we can actually have some interesting properties. We can integrate the inequality that we would construct from the definition of the MLSI constant, because the MLSI constant is in particular the optimal constant associated to the modified logarithmic Sobolev inequality. So when one integrates that inequality, we get an entropy decay, and this is why the title of this talk is Entropy Decay. And what we know is that we can estimate the entropy between the state after time t and the fixed point by the initial entropy at time 0 and some exponential decay with the time given by the rate of the MLSI constant. And this, when we put it together with Pinsker's inequality, gives an upper bound of this form for the one norm of the difference between these two states. And in particular, you see that here we have some factor that depends on the logarithm of the inverse of the minimal eigenvalue of sigma. But in our case, we are studying thermal states, so this is going to scale exponentially, well, minus exponentially with the size of lambda. So in particular, this is going to scale polynomially with the size of lambda. And then it means that when we have a positive MLSI constant, in particular, we have an example of rapid mixing. So this is a way to prove rapid mixing. And this is something that we have been using in the past years, because when we consider instead the spectral gap, Castoriano and Temes showed in 2013 that you get here this multiplicative term, which is, as you see, exponentially worse. And then in particular, this doesn't guarantee that you have rapid mixing. So that we can see this in a picture very fast, then this is exactly what I just said. So the MLSI constant, or a log Sobolev constant, implies rapid mixing. And it also implies spectral gap, but the spectral gap in general doesn't imply rapid mixing. And what we know is that rapid mixing implies certain forms of exponential decay of correlations, not every form of exponential decay of correlations. So here we have to be a bit careful. And what we are interested in studying now is which kind of exponential decay of correlations imply logs of Aleph constants, so that we can go from here to here and then to having rapid mixing. And rapid mixing is interesting for many reasons, but in particular, systems with rapid mixing have nice properties of stability against local perturbations and area loss for the mutual information. These are just some of their nice properties. And one of the nice things that I like about this scheme here is that it relates dynamical properties of the evolution of the semigroup with properties that only depend, that are static, so they only depend on something that happens on the fixed point of the evolution, which is usually going to be taken to be a Gibbs state of a Hamiltonian. And this only depends on the correlations between two separated regions. So if the convergence here happens very fast, then it seems that separated regions don't have enough time to correlate, and this is why the correlations decay very fast. This is a bit of the interpretation of this scheme. Okay, so what we want to do here is to prove, as I said, that certain exponential decay of correlations imply logs of Aleph constant, and for that, we have developed a strategy in the past years that we have been using in several works. And the idea is that this strategy is based on these 5 points and these 5 pieces of puzzle that I draw here. So, sorry, do you still have a problem with the, maybe now it's better, I think. Okay, sorry for the shadow. Yeah, so as I was saying, this puzzle is a combination of 5 pieces. 2 of them have to do with correct definition of some particular features that are going to appear during the proof. So one of them is some particular form of the decay of correlations that we have to assume on the Gibbs state so that the rest holds. And we also have to define properly some notion of conditional logs of Aleph constant or MLSI. And once we manage to do this properly depending on the physical system, then there are 3 pieces that have to be proven. So we have to prove some result of quasi-factorization. Then we have to prove some result on geometric recursive arguments. And we have to prove that some MLSI constant that is conditioned onto some small region is positive. And the idea of this is the following. So the idea is that, as I said before, we are interested on taking the thermodynamic limit of the MLSI. So the problem that we could have there is with the scaling. So if we have something that depends on the size of the lattice where we are considering the MLSI and we take the thermodynamic limit, this might explode. Or, well, in this case, go to 0. But the thing is that if we manage to reduce the information of the MLSI on a lattice lambda to a sublattice that has a fixed size, and then we manage to prove that this reduction, this conditional MLSI is positive, then we are done. So this is why we use this geometric recursive argument to do that. And a way to see this, I mean, as I just said, the conditional MLSI constant is just some modification from the MLSI constant. So the idea is that you want to provide some definition for the MLSI in this restricted subregion A of lambda. And then you define it in the same way than the MLSI constant, but now you're considering the generator only on A. And here you are considering some conditional relative entropy that we also have to introduce properly in each case. And once we do that, the idea that all these strategies are always based on, and so the key point is this result of quasi-factorization of the relative entropy that appeared in the puzzle. And this result is just an upper bound for the relative entropy between 2 states in the whole system, so now in lambda equals ABC, in terms of these conditional relative entropies that we have to define and that actually condition the information that you have into some small subregions of the lattice, and some multiplicative term that is going to be related to this decay of correlation on the Gibbs state. And the idea for this is the following. So when you have defined this conditional MLSI and you want to reduce your MLSI to the in the region lambda to the conditional MLSI on A, you see that the numerator is easy to reduce because these generators that we consider here are usually linear on the subindex. And then this part is going to be fine. Just to reduce lambda to 8, this part is going to be fine. And the problem, we are going to have it with the denominators, when we have to reduce this relative entropy to these conditional relative entropies. And this is why we have to engineer this method based on this kind of inequalities of quasi-factorization. So just to illustrate the potential of these techniques, I'm going to provide a very simple example. So, I mean, the simplest example that we have. And we had it for some model, that is the heat bath model that you will see later. And in the case in which the fixed point is a tensor product. So in this case, the generator is given by the term that I write here. So essentially you have a density matrix rho. You trace out the site X for this density matrix. You reconstruct it with the fixed point sigma. And then you see how far you are from the initial density matrix rho in lambda. And you sum over doing this over all possible sites X of the lattice lambda. This is how you construct the generator, and in this case, the conditional relative entropy in X is given, we define it as the difference between the relative entropy in the global system lambda and the relative entropy in the complement of X, so for rho and sigma. So when we take these definitions, we have to see how all these pieces of the puzzle enter together to provide that we have a positive MLSI. And the idea is that the first thing that we prove is that you have an upper bound for the relative entropy in terms of the sum of all the conditional relative entropies everywhere. So in all the sites X. So this is the part of the quasi-factorization. The part that we are assuming of decay of correlations is actually much more than decay of correlations, because it's just assuming that there are no correlations at all. So sigma is a tensor product everywhere. And now, because of the definition of the conditional relative entropy, we can write this inequality. We can just extract the infimum of all these conditional MLSIs, as we do here. And then the geometric recursive argument, which is not recursive in this case because of the simplicity of the geometry, is just using the linearity with respect to the subindex for the generator. And finally, what we have to prove is that the conditional MLSIs are positive, and we actually prove that they are larger than or equal to 1/2. So this is how you end up upper bounding the relative entropy between these two states by the entropy production, so the derivative of the relative entropy. And then if you take now quotient and infimum over rho, you are getting back the MLSI. So this is how you see, this is the simplest case, but this is how the strategy works, more or less. And now what we are doing is building on this strategy and providing examples for much more difficult dynamics and seeing how all these pieces behave in these cases. So before entering the main result that I want to present here, what I'm going to mention are some previous results that we've been developing in the last years, so that we compare more or less the difficulties, and we see how we have been overcoming these difficulties. So first of all, let me say that the fixed point is always going to be taken to be the Gibbs state of a finite range and commuting Hamiltonian, and depending on the case, we're going to be assuming more conditions. And we are always going to be working with three kinds of dynamics. So one of them is going to be the Hipaa generator, which is the simplest one to write down. So this has the nicest expression and then it's easier to compute things from it. And if you see the term that appears here, this is essentially what Cambyse was calling before psi sub b, I think. So this is the composition of the Petz recovery map with the partial tracing X applied to the state rho. And the Hipaa generator is defined like this, but it doesn't really have a lot of physical intuition behind it. So for more feasible physical systems, it's better to consider the Davies generator. But the main problem that the Davies generator presents is that it's much more difficult to work mathematically with it. Because even though you are assuming some things on the weak coupling so that you can simplify the expression of the generator to these terms here, and these terms behave in a particularly interesting way, it's still very difficult to work with them. So this is why we also have to consider the Schmidt generator, which also has some physical intuition, but now it's easier to write down because you can actually write it as the sum of some conditional expectations and the difference between it and the identity. And these conditional expectations, the most interesting thing that they have is that they don't depend on system path couplings, and actually they only depend on what happens on a region and some small part of the boundary, so they are easier to work with. And we consider these three models at the same time. So I'm going to go a bit faster here. The previous results that appeared on this direction in the last years are the following. First of all, let me recall the difference between estimating the one of the difference between these two states by an MLSI constant and by a spectral graph, which is given by these two inequalities. And then the first thing that we know in this breakthrough by Castoriano and Brandon in 2016 is that both the Hipaa and the Davies dynamics in 1D have a positive spectral graph that is independent of the system size for every temperature. So we know that this holds for these two dynamics in 1D always, and this is pretty good. Of course, we would like to lift the result to the MLSI, and this is what we are in the direction we are working in. And the first thing that we do is to consider, as I just said, the heat bath with tensor product fixed point. And I just briefly sketched the proof, and it also appeared in a paper by Bardet and Rouzé at the same time. And what we proved is essentially that the heat bath, but assuming some very strong condition on the fixed point, has a positive MLSI. The next thing that we did was to weaken the condition that you impose on the fixed point. So now the condition is a bit weaker. Now the idea is that this multiplicative term that appeared in some form of quasi-factorization has to be bounded. And this is something that we have to assume for this model. And we also have to assume that some strong form of quasi-factorization holds. I'm not going to go into details here on this, but let me just say that there are some examples for the first assumption. So at least Gibbs state at high enough temperature satisfy this. And for the second assumption, at least tensor product satisfy it. So, and when we assume these two things, then we could also prove that a k-local commuting Hamiltonian, I mean, if sigma is the Gibbs state of a k-local commuting Hamiltonian in 1D, then the heat bath dynamics also satisfies the positive MLSI. So this is slightly better than the result that we had before. Good. So now, instead of going to the Hipaa, that, as I said, is the easiest one to work with, but we are interested in working with something that has a better physical interpretation, we move to the Schmidt semigroups, which are a bit harder to work with, but as I said, you get something from the physics point of view. And there we actually managed to prove something that is quite interesting. That is that when you consider a Hamiltonian to be local and commuting again, but now also to be either classical or nearest neighbor, or just to consider a lattice in 1D, so just a spin chain. Then there is a local quantum Markov semigroup that has a fixed point, the Gibbs state of this Hamiltonian, that has a positive MLSI constant. And actually this quantum Markov semigroup, well, its generator is the Schmidt generator that I was introducing before. So this is why we started working with this kind of generators. And there's already a big gap with respect to the previous results. So these are much more involved, and it's already providing some interesting applications. So from there, it's from where we move to our main result here. And the main result that we present here is finally for the Davies generators, which is what we were aiming for from the beginning. And this is something that is probably going to appear on arXiv in the next weeks. And the idea now is that we also have to assume that the Gibbs state is of a Hamiltonian that is commuting finite range and translation invariant. So this is something new that we have to assume. But still, we can prove something at any temperature in 1D. And what we can prove is that this generator satisfies a positive MLSI. Now it's not independent of the system size. So now it depends logarithmically with the system size, which is a bit bad, but not really bad. Because the thing is that we were interested in proving rapid mixing. And remember that rapid mixing was given by this expression here. So now, if you replace this logarithmic dependence with the system size here in this exponent, then we still have some polynomial dependence, some polynomial growth with the system size. So this is still good. And this still means that in the setting that I introduced here, we have rapid mixing. So this is what we were looking for, and then we are happy that at least we managed to prove this positive MLSI. And in the few minutes that I have left, I'm going to briefly sketch the proof just by showing how these pieces would interact here. So the first thing that we have to do is take two different conditional relative entropies. There are the one that I mentioned before, and another one that compares one state to applying a conditional expectation onto a subregion on that state. For the first one, we proved in the past that this result of quasi-factorization for the relative entropy holds. So we could prove an upper bound for the relative entropy in terms of the sum of these two conditional relative entropies. And now the multiplicative error term that we have here is given by this expression that measures in part how far sigma is from being a tensor product between A and C, as you see. And now we apply this to the particular 1D model that we are studying here. So we consider a 1D change like this one, and then we split it into small segments of this form so that they overlap pairwise, and the overlap is always of the same size and the segments all have the same size. And then we call A the union of all these AIs and B the union of all these BIs, and we apply the result of quasi-factorization to A and B there. So then we have this inequality. But as I said before, we want to reduce the MLSI of the global lambda to MLSIs of fixed regions. And you see that now if you make lambda grow, you have more AIs and more BIs. So this is not good enough. We would really need to reduce these terms in the right-hand side to the AIs and the BIs. And this is actually something that we can do because sigma now is not a tensor product as before, so it's not as easy as before, but it's a quantum Markov chain. And this is why we are assuming that this is commuting, so that the Gibbs state is a quantum Markov chain. So now sigma is a quantum Markov chain between AI, the boundary of AI, and the rest. And because of that, it behaves as a tensor product between AI and the other AJs. So then we can split the conditional relative entropy in A in the other conditional relative entropies everywhere in all the AIs. And by combining these two results, we have this inequality with this multiplicative error term. And now we have to estimate this multiplicative error term. And even in the classical case, it was complicated because if you see, now we have for the distance between A complement and B complement, which can be drawn in this picture as the pink and the blue parts, we have a lot of greens and yellows if you continue the picture. So you have to count all these distances in the estimation for this node. And then this is a problem because even in the classical case with the result that they have for this mixing condition, this would scale very bad. But thanks to a result that Antonio presented yesterday in his talk, that was essentially that the norm of sigma, I mean, in this picture here, x, y, z, if sigma x to the -1 tensor sigma z to the -1 and sigma x, x z, the distance between that and the identity, the fact that it scales with the size of the middle system exponentially, I mean that it decays with the size of the middle system exponentially. Thanks to this result, we can apply it recursively to estimate properly the term that we have here. And what we obtain as a consequence is that this error term is uniformly bounded as long as the number of segments is taken in a proper way. So like of order of cardinality of the whole spin chain over the logarithm of the same. Good. So just to mention the two steps that are left, one important thing that we have now that we didn't have before is that we can compare the two conditional relative entropies that I was mentioning before and in this form, so that now if you apply this inequality to the inequality that I was writing in the previous slide, putting everything together, we have an upper bound for the relative entropy in terms of the sum of all these conditional relative entropies with the conditional expectations and this multiplicative error term that now we know how to control. And the only thing that is left to do, because now we have reduced the global MLSI to the conditional MLSIs in the small regions, the only thing that is left to do is to prove that these are actually positive and behaving in a proper way, so scaling properly with the system size. And for this is where we use the techniques that were introduced in this talk this morning or night, depending on when you are. But it's where they were talking about positive CMLSIs, so complete MLSIs. So in this paper in 2021, Lee and Cambyse, what they did was to, one of the results that they had there was to reduce the relative entropy between a state and a conditional expectation on a segment applied to this state to actually all the conditional, all the conditional relative entropies for these conditional expectations, but on every site J. And then it's very good because all these terms, when defining the conditional MLSI on each of the local generators, so on each of the sites, they managed to prove that this is positive. So what they did was to reduce this to this, and then you would reduce the conditional MLSIs in AIs to the conditional MLSIs on each site. And the only thing that was left to do was to estimate properly these multiplicative constants that appear here, And the last thing that we do in the paper is to see that actually they behave properly because they scale in this form with respect to this lambda, and lambda is a constant that is associated to the spectral gap by the detectability lemma. So the idea now is that using the result by Castorian and Brandau, in which they proved that there is gap, we can lift the result. So we can lift the existence of gap to the existence of CMLSI, and putting everything together, we have our MLSI. So this is how all the puzzle comes together. And then the only thing that is left to do is to see where the Davies is coming from, because everything that I've been mentioning here is for the Hipaa dynamics. But the thing is that the conditional expectations associated to both dynamics were proven last year to coincide. So then everything that we've done here for the Hipaa dynamics was actually for the Davies dynamics. And then we can conclude that we have a positive MLSI for this generator that scales logarithmically with the system size, and therefore the generator has rapid mixing. And let me conclude by wrapping up by saying that what we've done in this talk has been to use results of quasi-factorization and decay of correlations to prove MLSI. And we have shown how all these pieces and different techniques from the past few years can be put together to prove some results of MLSI for relevant physical systems in 1D. And there are, of course, many open problems from here. Like, for example, the most interesting thing would be to prove something similar for a positive MLSI constant that is actually constant, so it doesn't depend on the system size, but I think this is going to be quite hard. And of course, we would also like to extend this to more dimensions, but this is an open problem for the moment. So thank you very much for your attention.
Thank you, Angela, for this very nice talk. I saw there's a question from the chat room from Esteban. Could you explain a bit more about the benefits of rapid mixing?
Can you read the question, or should I look for it?
Esteban asked, could you explain a bit more about the benefits of rapid mixing?
Sorry, explain a bit more about what? I couldn't hear you.
Rapid mixing.
Rapid mixing. Okay, explain a bit more about why it's interesting, or why, or how it's constructed. Well, I guess possible features why it's interesting. As I said before, it's because it has some nice properties. So the idea essentially is that maybe it's easier with the picture. The idea essentially is that when you have an initial density matrix on the system, it's going to be almost indistinguishable from the fixed point of the evolution very fast. So the idea is that it's going to be very close to sigma very fast. And this is going to destroy the correlations far very fast. So because of that, these kind of systems, for example, are stable against local perturbations, because if you perturb, these perturbations are killed very fast. And also because of that, is why it satisfies some AD from the mutual information and all these desirable properties.
Okay.
I don't know if this was.
I think since we are over time, so we can move on to the Slack channel for further discussion. So let me thank Angela again for this very great talk.
Okay, thanks a lot.